into rasters for further processing. To do that, to make that conversion, we use again ArcToolbox, the conversion tools toolbox, expand it to define the to raster toolbox, and within that toolbox we will see the feature to raster tool. So we can rasterize the fire perimeter. Then we need to apply some map arithmetic, a logical operator to begin with. We need to find all the slopes, all the pixels with a slope greater than or equal to 30%. We use the Spatial Analyst toolbox, expand it, locate the math toolbox, logical toolbox within that, and then find the greater than equal tool. And that will allow us to produce a output layer that we're simply calling slope GT30, greater than 30, or GTE 30, greater than or equal to 30. Another part of our cartographic model asks us to calculate the product of fire's raster, so the rasterized version of our fire's polygon, the rasterized version of it, multiplied by slope greater than or equal to 30, whatever. And that will produce a landslide susceptibility layer. Now, why are we doing this? Perhaps we should pause for just a minute to figure out how this is working. The fire's raster layer is a Boolean layer, meaning that all the pixels outside the fire perimeter have a value of 0. Fire didn't occur here, it's false. All the pixels inside the fire perimeter have a value of 1, true. A fire did occur here. If we multiply that raster layer by slope greater than or equal to 30, which is also a Boolean layer, all the pixels that satisfy the expression slope is greater than or equal to 30 have been given a value of 1, true, and those that don't satisfy the expression have a value of 0, false. So if we multiply those two layers together, what we're going to get is we're going to find all those areas, all the pixels that, 1, were within the fire, and 2, have a slope greater than or equal to 30. So they satisfy both parts of the expression. How could we do this using not an arithmetic operation or mathematical operation? How could we do this with a logical operation? Well, if we do an AND, that would essentially give us the same result. Fire raster and slope greater than or equal to 30. We can automate these tasks. If we need to convert 50, 100, whatever, even 10 vector layers to rasterized versions of those layers, we can use the batch tool. Find any tool that you want to use in ArcToolbox, right-click that tool and choose batch. That will then bring up essentially a table for you to fill out. Input features, the field that you want to rasterize on, so on and so forth. Once you complete that, filling out that table, you can click OK and let it process. And it can do a lot of processing very, very quickly for you. You can do essentially speed fills on some of this stuff, so you don't have to type out all that information yourself. This is a very, very handy tool, the batch tool, and I encourage you to explore it when you have the opportunity. Let's look at the model builder just a little bit. On the left side of this screen, we're looking at our cartographic model, the paper version, if you will, of how we were going to walk through each step of this process. And on the right side, we have a essentially live version of the cartographic model. This was built in ArcGIS, and we can not only see essentially the same thing, how this process is going to be performed, but this model can be run. This same process can be completed, or was completed, in 15 seconds. So while it took me several minutes to describe the process, and it would take us quite a while to click through that entire process, by setting up the model once in the model builder and then executing that, we had it completed in 15 seconds. Now, of course, it takes a little while to set that model up in model builder and debug it, make sure it's working just right. However, if you're going to be doing iterative processing, model builder is a great tool, because you know that each iteration is being processed exactly in the same way. Understanding error. Understanding error in GIS is critical for the proper use and application of GIS and the results that we get from GIS. There's 3 parts to understanding error, 3 very important parts. The first is identification of error, looking at your data and your processing and understanding where errors or biases creep into your GIS and your individual research project. In some cases, the identification of error is pretty darn difficult, especially when we get to the second step, which is error quantification. Okay, so we know that we have some error here, there, whatever. Now we have to figure out how much error do we have. Meaning, is it a locational error? If it's a locational error, is it plus or minus 1 centimeter, plus or minus 10 meters, these sorts of things. And the third part is error propagation, and that is where we take a look at the sum effect of all the errors and biases that we have identified and quantified in our research, and try to figure out how different the end result will be based on the incorporation of all these sorts of errors. Ideally, once we go through the identification of error and the quantification of error, and then we run through an error propagation exercise, ideally the end result is always just about the same. The answer doesn't change. It doesn't matter. Yes, we have error here and error there, but we're still getting the same answer. That's ideal. That's fantastic if we get that. We have a high confidence in the results of our GIS. Many cases, though, that's not true. When you run through your error propagation exercise with your individual research project, what you find out is that, because of all these errors that I have in my data and my modeling and my processing, the answer is not always the same. So then you have less confidence that any individual answer that you might provide as part of your project results or thesis or whatever it happens to be, you have less confidence that that is really the correct answer. We'll talk about this in far greater detail next week when we focus on understanding error and uncertainty in GIS. So are there any questions?